ELCT201 End of Semester Project, Visual Audio Spectrum. I'm Ian McElrath.
I'm Alden Thurl.
And I'm Lawrence Began.
The objective of this project was to build a circuit that displays the audio spectrum using lights.
To do this, we used filters, optocouplers, and triacs. The filters separate the audio spectrum into high, mid, and low. The optocouplers isolate the DC voltage from the high-powered AC voltage, and the triacs actually switch the 120 volt on and off.
Our material list included
to 10 volts peak to peak. We calculated our R1 and R2 values. R2 was a 10-turn pot. The equation to calculate the gain is gain equals 1 plus R2 over R1. We wanted to go from our output of our audio, which was 2 volts, to our 10 volt peak to peak value that we were aiming for. That gave us a gain of 5. We set our R2 value to 10K, which was our maximum value of our 10-turn pot, and just calculated R1 based on those values. We got an effective gain of 5.17 at the maximum of the 10-turn pot.
the audio filter portion of our circuit consists of a high and low pass second order Butterworth active filter. The Butterworth filter is a unique filter that's engineered to have a maximally flat frequency response. When observing the high pass second order active filter, Butterworth filter, it's observed to have a 40 dB per decade roll off and to have a gain of -3 dB. Its phase shift starts at positive 180 degrees and its angle cutoff is at 90 degrees and rolls off at 0 degrees. Here we observe the low-pass Bode plot for the second order low-pass active Butterworth filter. Here we're observed to have a roll-off of -40 dB per decade and also have a -3 dB gain on the low-pass filter, just like the high-pass filter. We observe the phase shift to start at 0 and to run through -180 degrees with its phase shift angle at -90 degrees. An optocoupler is a unique electronic device that is used to separate voltage sources in circuits. In our case, we utilized it to separate the 120 volts used to power our 2 lights and the 12 volts used to power our filters. What we have is an infrared light shines onto a photo transistor. Now, this side of the LED would be attached to our 12 volts. As current is applied to the LED turns on. Infrared light shines on the phototransistor. The phototransistor closes and allows for current to flow and have our lights turn on.
A triac is a unique component that's used for switching AC voltages. It's essentially 2 thyristors connected in anti-parallel, and then there's a gate that is used to turn on and off the thyristors. This is a circuit shown with the 2 thyristors and the gates tied, and then this is our triac circuit, which is an equivalent, just in a neater package. To build our circuit, we separated into 4 subsystems. The first of the 4 subsystems is our audio input amplifier. We just used a non-inverting amplifier with a gain of 100 to amplify the signal from a millivolt peak to peak to 10 volts peak to peak, so that our amplitude would be large enough to power the filters and the triacs.
The second subsystem of our circuit is the low-pass filter and the high-pass filter. And our audio signal is coming into both filters. The filters are connected in parallel, That way they're not both operating one after the other. And we scaled our low pass filter to cutoff frequency of 85 hertz. And we did that by changing resistor values and capacitor values. For our high pass filter, we have a cutoff of 2,126 hertz. And the output of these filters goes into the optocouplers and the triacs.
In our third phase, we implemented our optocouplers, which connected our outputs from our two filters to the gates of both triacs, connecting our lights.
The fourth subsystem of our circuit involves two triacs that are used to switch on a red light and a green light. And those lights are both powered from the 120 volt AC.
Here's the inside circuit of our project. Here's the audio amplifier subsection, the low pass filter section, and the high pass filter section, and those are connected to the perf board.
From the perf board, we actually built our optocoupler and triac circuits, and then that actually runs the power to our lights, which are mounted up above the junction box.
In conclusion,
This is our final project. We have our low pass and high pass filter operating with the audio in.
We did run into a few snags along the way. We had originally tried to run the circuit without the optocoupler, and we ended up backfeeding some voltage into the power supply. So if we're using triacs from now on, we'll be sure that we have an optocoupler included in our circuit. But
Other than that, I think just the scaling of the filters, we had to adjust them according to what we wanted to show the audio spectrum. In our project, we had some extra time, so we went back in and put a narrow bandpass filter in. We set our center frequency of this filter to be 500 hertz, and we adjusted it to where you have 100 hertz on each side of that center frequency. So it goes down to 400 hertz and then up to 600. And here you have your audio in coming in to the filter, and then you have your output of your narrow bandpass filter.